talking about mass spectrometry. True or false? Mass spectrometry relies on light.
False.
False.
Cannot be evidence. Cannot be the weighted question.
What we established yesterday was, oh, you know what, when I do true-false questions, if you guys have done the old study materials, you'll find my old homework problems have true-false. But they're actually, if false, change the bolded words to make it true. No, it's not change the sentence to make it true. Change the bolded words to make it true. So it's like, it would, true or false, mass spectrometry, bold, does use light. And then you would say doesn't use.
False, and then cross it out.
False, doesn't use light. Or would maybe say like uses a magnetic field. Because remember, that's what we said yesterday, is that a sample comes in and is ionized and forms radicals and cations. And the cations are then directed by a magnetic field where they hit a detector, and radicals are unaffected by the magnetic field, and the radicals are just sucked into the waste. So that was our setup. And what we're going to look at today is the spectrum. What is produced? The y-axis of our spectrum is relative intensity. Which means that the numbers are a bit meaningless, or another way to say that is the numbers are normalized. So we don't look at it and say, what is that peak going to? We just say, how tall is that peak relative to all of the other peaks? So whatever the tallest peak is normalized to 100% relative intensity. And that tallest peak, wherever it shows up, is referred to as the base peak. It has 100% relative intensity. Relative to that peak, it is the most abundant.
The base peak is always at 100%.
Yeah, always. Because it's relative, it's always normalized to the height of the base peak. The x-axis is m per z, which stands for mass per charge. What is the charge that something hitting the detector typically has? Positive 1. As opposed to positive 2 or positive 3, because if I have a fragment of a certain mass and it collectively has a +1 charge, my magnetic field has some force on it. But if that same fragment, the same mass, has twice as much charge, my magnetic field has twice as much force on it. We're thinking of these as magnets, right? And a +1 magnet is weaker. A +2 magnet is stronger. And remember the way that I was depicting this detector is if the fragment hits the detector on one side, that means the magnetic field couldn't really pull it well. And so the detector knows that it's heavy. If it hits the detector on another side, that means the magnetic field pulled it really well, and that means the fragment is light. If I have a fragment that has a 2+ charge, it's going to hit my detector at a place where the detector thinks it's half the mass because of how easily it pulled it. This is not necessarily the mass of what's hitting the detector. It could be the mass divided by 2 of what's hitting the detector if one fragment has 2 electrons picked off of it. 99% of the time, we're looking at mass per charge, where charge is +1. So 99% of the time, this can be thought of as atomic mass units. It's not, the x-axis is not atomic mass units. It is strictly mass per charge. But because the charge is 99% of the time +1, that means that 99% of the time, whatever the number is on the x-axis is the atomic mass units of the fragment of the sample that hit the detector. So we get mass out of this, and we get a spectrum of mass. One of the most important signals that we generate is called the molecular ion. We abbreviate the molecular ion as M+. M for molecule, and then plus for the fact that it has lost an electron and is now positively charged. But what did we say we could call this? We could call this the mother ion. It is the molecule that has not lost any of its mass yet. And if it did lose mass, we'll call those daughter ions later. The molecular ion can form by, well, first let me say, this produces the highest mass per charge signal on the spectrum. I can't get a heavier mass to hit the detector than the entire mass of the molecule. And it forms by one of 3 ways. So first, let's say that we have a compound, and let's use benzoic acid, which is given to us in that first structure. We have a compound that has lone pairs. How many lone pairs in benzoic acid? Let me give you some options. How many lone pairs of electrons in benzoic acid? Take a few seconds, don't answer it yet. How many lone pairs of electrons in benzoic acid? Delaney? Chloe? Andrew?
I think it's 8.
8 lone pairs. Patrick?
I was going to say 4.
Saray? 4. Quinn? 4. Kayla? 4. Anybody want to back Andrew? They have 8 total electrons, or 8 total non-bonding electrons, grouped into 4 pairs. The key word there is pairs. Yep. All right, so there's 4 pairs of electrons, which means that I could show the loss of a lone pair electron from a lot of different places. I'm going to show it coming from the lone pair of the OH, just for the example. So if this molecule interacts with the electron beam and it loses an electron, what I am left with is a radical and a cation. In this case, it's a radical and a cation on the same atom, which means the radical is not going to be lost to the waste because the radical is a part of the cation, which will get dragged to the detector.
So it'll be an O plus H?
It is, yeah. If we didn't draw in the lone pairs, and if you remember that we can abbreviate the aromatic ring as pH, we could draw it like this. I still drew that radical because bond line structure said we can assume lone pairs, but we shouldn't assume anything but lone pairs, right? That's not a lone pair anymore, is it? It's a radical, it's an unpaired electron. So we show that as well. This has the mass of the structure, and it will hit the detector. So it will give the highest possible mass per charge reading. And that mass per charge reading is, well, I've got this aromatic ring where I've got 6 carbons and 5 hydrogens. So 6 times 12, because the atomic mass of a carbon is 12. 6 times 12 is 72. And 5 is 77. If you look at your correlation table for mass spec, you'll actually see that if you have just an aromatic ring fragment, it shows up with a mass of 77. Then I have another carbon, so 77 plus 12, 89. I have 2 oxygens and a hydrogen, so that's 16, 16 and 1, 33. So 89 and 33 is 90 to 122. The mass of benzoic acid is 122 atomic mass units. And so when I put a positive charge onto that fragment, it hits the detector at 122 mass per charge. Let's look at the spectrum. Do we see a signal at 122? Does anybody need a spectrum sheet? Okay, sorry.
Sorry, I didn't realize that.
That's okay. Did I hand these out last class?
No, not this one.
Oh. That explains a lot. You're welcome. He's got one. Oh. Good. Yeah, here I am like, look at the spectrum, guys. Come on.
You missed one right here.
Sorry. Thank you, Andrew. Do you see? Okay, well. We're not looking at the very top spectrum. We're looking at the one just under molecular ion and base peak. Do you see a signal on the spectrum at 122 mass per charge? Sure do. Sure do. Is it the base peak?
No.
It's not. It's close to it. It's like one of the most abundant signals, but it's not the most abundant signal. So that signal on your spectrum you can label as N+. And this might be how it got there. But we can also form it by the loss of a pi electron. How many pi bonds are in benzoic acid? 4 pi bonds. So any of those 4 positions, I'm going to show you guys one, and then I want you guys to try and draw another. I'm going to take the pi bond of the carboxylic acid, and I'm going to say that we lose one of these electrons because of the ionization chamber, the electron beam. And since my pi electrons are shared between oxygen and carbon, and one of them is being removed, where will the remaining electron be? It will be on oxygen, because oxygen is more electronegative. So a radical on oxygen, which means carbon has lost one pi electron to the ionization and the other pi electron to electronegativity. You guys agree? Carbon essentially lost both of its electrons. So now carbon is sitting there with a positive charge. And what's the mass of this structure? Not a hydrogen has been lost. Not a bond has been broken that creates two structures. This still weighs 122, and it hits the detector at 122 mass per charge units.
And we took we broke that pi bond because it wasn't part of the ring and it's easier.
I want you guys to now break a different pi bond and show a different molecular ion that forms by loss of a different pi electron. Deal? Take a minute. You've got 3 other options for what it could look like. Draw a different molecular ion by loss of a pi electron.
Some days I'm like, this is great. Okay, so.
Close. Not quite there yet. Do you see what you're missing, Rowan?
Single electron.
Uh-huh. If it helps, draw in those hydrogens that get assumed. Draw another molecular ion by loss. Draw another molecular ion by loss of a different pi electron. I showed you the loss of the CO pi electron. Show me the loss by a different pi electron.
Are we right or wrong?
Wrong, but close.
What's wrong?
You have a CH2 in the ring, and there were no CH2s in the molecule.
Mine might be wrong.
Yours has no radical.
That's not radical.
Yeah, look at this. Molecular ion is a radical cation. Molecular ion is a radical cation. Your structure had a cation. I didn't see a radical. There you go. That was it.
So then, sorry, would the charge go through like one of these since like the
On one, but not the other.
on one but not the others?
Before you drew that in, your bond line structure said CH2.
Yeah, so I needed to account for that last electron.
Exactly. Not quite. You have, well, first of all, they wouldn't have a charge. This carbon has 1, 2, 3 bonds, one of them to the hydrogen, and it has 1 electron. So if you did the formal charge calculation, that's dots plus bonds, dot and 3 bonds, 4 minus 4. If they both have a radical, then they're not charged. And if they both have a radical, you haven't actually lost any electrons. You just took the pi bond, split it into radicals. Did I show yours yet? No radical. Where is the radical? On the same carbon?
On the different.
On the other carbon. Great. We're drawing another molecular ion by loss of a different pi electron. Good. Perfect. Yes.
So does it have to come from?
A pi bond.
Yeah, but can it come from like one of these ones?
Yep.
Why was the thing I drew wrong?
This is also wrong.
Oh, cool.
So it's wrong.
Why is this wrong?
Wrong for the same reason I think as last time.
Will
Because
the radical and the cation be in a different spot?
yes.
Okay.
Look at that. The radical and the cation are in different spots.
Oh, I need that here and my radical here.
Yep.
So, okay, so you can, the radical
Oh, I
accounts
didn't
for
know.
the missed hydrogen in the CH2. That way it's not a CH2, it's still a full
Correct.
guy.
Correct.
And then that is because the carbon doesn't have a double bond anymore.
Notice how the radical position isn't charged. This radical is neutral. This radical is charged, but this radical position is neutral.
You were right, you have to have the.
So the other options that you could get here, if I take this pi electron, or sorry, this pi bond, I could take a radical on the top carbon and a positive charge on the bottom. But because I'm splitting between carbon and carbon, my radical also could have been on the bottom carbon and my positive charge on the top.
So either or could be correct.
Correct. And that was just one of the 3 other pi bonds. So there are a ton of other options here where a different pi bond gets split, and again could get split in 2 different ways. Notice how the carbon holding the radical is neutral, because if you do the formal charge calculation, 4 minus 3 bonds plus 1 dot. 4 minus 4 is neutral. The radical carbon is neutral. The main mistake that I saw you guys making in doing this, well, for one, you would do something like this, which is not a radical cation. The molecular ion is a radical cation. It's not a radical plus a cation. It is both. It's not 2 separate things. It's both of them at the same time. This doesn't have a radical, so it can't be a molecular ion. And a fatal flaw. You've added a hydrogen to a carbon that did not have a hydrogen before. Now, a lot of you actually drew it more like this, and so you were creating a CH2 group in a molecule that had no CH2 groups. That was the downfall that I saw most of the places. No radical, which means you're actually creating a bond to a hydrogen somewhere. All right, lots of possibilities there, which is one of the reasons why the molecular ion for benzoic acid is so tall, is because there's a lot of different ways that it can form. So they all form and they all hit the detector and it gives a loud reading. The last way that I can form a molecular ion is by loss of a sigma electron. And there's a lot of sigma electrons. So I'm going to show the loss of a sigma electron between the aromatic ring and the carbonyl carbon. Remind me what a carbonyl carbon is again? Good, the CO double bond. So I'm going to take the electron, 1 electron, from the bond between the ring and the bond outside of the ring. You ever seen a 1 electron covalent bond? They do exist. They're not very common. Actually, one was just reported, I want to say last year or the year before, a very important 1 electron covalent bond between 2 carbons. That's a 1 electron covalent bond. Notice that the radical is not held by one position and the positive charge is not held by one position, but there's just a net positive 1 and a 1 electron covalent bond. I can't draw a line because a line represents 2 electrons. and there's not 2 electrons, so I just have to draw a radical between the 2 atoms sharing the electron. Stable? Not really. In fact, if this does form, it still travels all the way and it hits the detector at 122 mass per charge units. But if it gets disturbed anywhere, then it is unlikely to actually travel all the way. And so we move now from the molecular ion to the back side. I'm sorry, we're not looking at the one below it. I think I might have us come back to it. Daughter ions. Tell me.
We were just wondering how you got the 122 if you manually added the AMU bits.
I did it in my head,
Oh, God.
out loud, but you don't have to.
Okay. But you do have to do it.
Well, you'll notice on the correlation table that a lot of them are listed. A lot of common fragments are listed. And we'll talk about common masses, like a methyl group. Carbon of 12 and 3 hydrogens. A methyl group weighs 15.
Yeah.
Now every time you've got a methyl group, 15, 30, 45, 50, 60. Just like the clock. A CH2 group weighs 14. A CH group weighs 13. An OH group weighs 17. So there are some common mass fragments that you can just get used to. One thing that I said, the correlation table tells me that the aromatic ring weighs 77, assuming that there's no hydrogen. So that's 77 plus 32, 1, and 12. You are allowed to bring a calculator to the midterm, but I rarely see students need a calculator on the midterm. This would be the only thing you might want it for. It's not really that necessary. Now, if we call the molecular ion M+, then we can refer to these daughter ions as M, the molecule, minus some number. And so I want to stick with this idea of benzoic acid in its totally stable sigma electron loss. This is like trying to get my marker to travel down the length of I-15 from Bountiful to Provo like this, just next to each other without actually being connected. The smallest amount of disruption, and they're going to separate. How will they separate? That electron has to go to one group or the other. And the positive charge then will be left in the wake with the other or the one. So 2 possibilities from here. Every time we cause a fragment, every time we cleave the molecule to have an ion that is not the entire molecule, but just a daughter of the molecule, a fragment of the molecule, every time we do this cleavage, there are 2 ways that it can happen. Imagine that the ring takes the radical, which means that the carbonyl carbon has taken the positive charge. It's now a fragment of the molecule that is a radical and a fragment of the molecule that is a cation. It's now a radical and a cation, not a radical cation. You see the difference? The molecular ions were radical cations. The daughter fragments are radicals and cations. Why the heck is my carbonyl carbon drawn linear? Because it's neutral? Did someone say? The charge makes it linear. Wasn't it trigonal planar before? So why did I go from drawing it trigonal planar to drawing it linear? I lost an electron region. Right? That carbon used to have 3 regions. How many regions does that carbon have now? Just 2. So those 2 regions will arrange themselves 180. What's the mass of this cation? The radical goes to the waste. The radical isn't picked up by the detector because it has no charge. Can't divide by 0. What's the mass of this? 16 plus 12. I'm sorry, that's too hard for me. 16 plus 16 is 32. 32 plus 12 is 44. Plus the 1. Is it 46 or 45? This, in theory, would have a hit at the detector at 45 mass per charge. Do we see anything at 45? The tiniest little thing. I do have a signal at 45, but it's not a major signal. The other option here is that the ring takes on the positive charge, and the carbonyl takes the radical. Notice how it went back to its trigonal planar geometry, because now it has a 3rd electron region. The radical is the 3rd electron region, which means this fragment goes to the waste. And my remaining fragment hits the detector at 77 mass per charge. Do we see a signal at 77? It is. It is the second. It is the next biggest signal, is at 77. And I know it's kind of hard to read it in there, but it is a signal at 77. So we can name these signals. The signal at 77 is the mass of the molecule less 45 atomic mass units. And that's how we can represent the signal at 77. It is the molecule less 45. 122 minus 45 gives us this 77. What about this signal at 45? What could we have labeled it as? The mass minus 77. The molecule less 77. And of course, these are connected to each other. One forms because it was just the alternative of the other. All right, I do want to point out that the molecular ion of benzoic acid, 122 to 106, that's a loss of 18.
What, 122 to 106?
Yeah.
No.
Oh, that's because it's 105, which is a loss of 122 to 105 is a loss of 17. And you know what weighs 17? OH. So just the last thing here for benzoic acid's base peak. Which is a base peak at 105 mass per charge units, or in other words, M minus 17. I must have lost OH. Where do you think that OH came from? It's fine. You don't actually have to answer. So here's the deal. If I cleave off that OH, there's 2 possibilities of what forms. Remember, anytime you cleave a bond, the radical might end up on one side or on the other. So what I've done is I've cleaved the carbonyl to oxygen bond. I've cleaved the OH group, which means the carbonyl can either take the positive charge or the carbonyl can take the radical. Which of these structures produces the base peak signal? A, B, both, or neither? Got one vote for A. More votes for A. A lot of options there. A only, B only, A and B, neither A or B. Saray, you want to justify it? Exactly. The magnetic field has no impact on this radical fragment, which does have a mass of 105. It doesn't matter that it has the correct mass. It doesn't have any charge. So this doesn't hit the detector. It certainly doesn't give a reading of 105 mass per charge, because the charge is 0. So only A produces the M-17 signal. And it forms that because of the loss of that hydroxide radical. The OH radical is kicked out, and everything else then has a mass of 105. And you're okay with the idea that I've drawn that carbonyl linear? You want to see something cool? That is a resonance form. It's a 2-electron resonance. There's an atom with a lone pair adjacent to an atom with a positive charge. So it's in resonance. Resonance, remember, is a stabilizing phenomenon. It delocalizes charge and makes things more stable because of that. Which of those two resonance forms is a major contributor to the structure? Which of those resonance forms does the actual molecule look a little bit more like? Saray says on the left. What's your rationale for that? Carbon doesn't take the charge. That's all you're going to say too?
I mean, yes, and that is more stable.
Do you remember our 3 rules for resonance? First, minimize formal charge. Both of those resonance forms have the same formal charge. Second, maximize octets. And that really just means give carbon as many bonds as possible. Carbon lacks an octet, carbon has an octet. Oxygen has an octet, oxygen has an octet. So I'm maximizing octets when carbon has its full octet. So this is a major contributor to the structure because it maximizes its octets. You didn't think we were done with resonance, did you? We're just getting started. Okay. I want to take us back to the first page, and I would like you guys to draw a molecular ion for cyclohexane. Find cyclohexanes. Well, I guess I don't know that you need to do that. Cyclohexane C6H12. That's a mass of 84, and we can see that it has the molecular ion signal at 84. Can you draw me a molecular ion structure?
How do we know which one is the molecular ion again?
It's the mass of the molecule.
Oh, and we have the molecule. I didn't see that.
That's true.
Is it always the furthest?
I wish. Because sometimes the molecular ion isn't very stable and doesn't last long enough to hit the detector. So in theory, the molecular ion is the heaviest mass ion, the heaviest mass signal. But sometimes it doesn't really show up. So you can't just look at a spectrum and identify it, because it might not be there. But since we know the molecule weighs 84 AMU, and we know that because 6 times 12 is 72 plus 84. Sorry, that's not H12. It should be C6H12, not C6H14. 72 plus 12, 84. You got a structure for the molecular ion? For this guy? Nice. Molecular ion.
Yeah, it's really that simple, because there's no lone pairs, there's no icons, we have to be safe.
Tell him, Delaney. There's only one option. Yeah. That's, well, okay, when I say there's one option, there's actually as many options as there are bonds. So there's a lot of options, but there's really just one option. Good point. Very good point, actually. I'd never thought of looking at it like that. Yeah, actually, I quite like that. Yep. Great. Nothing yet? Don't want to write it in pen and be wrong?
Yeah, I'm scared.
Okay. I think I see your radical. I see your radical. See your radical. Did I see yours, Andrew? Yeah, I think I did. Okay. No cation there. Let's not have them be separate. Let's make one structure. So I redraw my ring, except I don't show one of the bonds, because one of those 2 electrons is going to be lost, and one of them will remain. So I have basically a ring, except I can't show a covalent bond between the last 2 carbons. Kayla did something very interesting, which probably is one of the reasons why the molecular ion for this ring is so intense and why it's so stable, is that even if this breaks and one carbon takes the radical and one carbon takes the cation, they stay on the same structure. They just go from a ring shape to a linear shape, but it's still a radical cation. But this is exactly how I expected you guys to draw it. This is not different. It's really just a different perspective, a different form. But what other options might have existed? Drawing a bond between carbon and hydrogen having lost its electron. I don't like it either, Liana, but it's a possibility, right? Where one of the CH bonds got cleaved. Okay.
Would that still be right?
I would say less likely, because it's very likely that this then splits apart. And we know that carbon is more electronegative, so it would probably take the radical. And hydrogen then, I don't even think this goes down to 1 mass per charge. So you wouldn't even see the H plus if it hit the detector. This, I think, is much more likely because it actually, even if it breaks apart, it stays together.
So then it takes the radical with it to the detector?
Well, yeah, because it's on one of the carbons. Yep. All right. So let's move back to the backside. And we've got this sec-butyl alcohol, or 2-butanol.
Can you show what the base peak for that one would look like?
No. Okay, so you guys see that the base peak is at 56 mass per charge units. with a ring like this, to get M minus, what would that be? M minus 8, M minus 28, to go from 84 down to 56. M minus 28, I'd have to lose 2 CH2s. 28 is 14 plus 14. 14 is 12 plus 2. So I'd have to lose 2 CH2s. So probably to get a signal at 56 by loss of 28, what I probably would be seeing is the ring gets cleaved here and here around the same time. Maybe one molecule gets hit twice, and then I'm left with a radical cation that has lost CH2, CH2, which itself could be a radical cation. So if I have a signal at 56, I might also have a signal at 28, M minus 56. Do we have a signal at 28? Barely. Very small one.
Wouldn't it have to be equivalent to the base peak?
No, yeah, you'd think, right? But no, they don't always have to form in equivalent ways. What I'm trying to say here is that ring structures can go through some strange rearrangements and like strange cleavage. So I'm not always going to ask you to be able to predict a base peak structure. I would only ask you to predict a base peak structure if it's obvious what has been lost and obvious how to get there. This is a very challenging, this is for when you go in to take instrumentation as a class, when you take spectroscopy as an upper level class, you can talk more about this. Your problems will be a lot easier. Saray. Yes, just like we said, it's possible for the signal to be mass per charge and the charge is +2. So the mass that you think you're getting is actually half of the mass because the charge is twice the charge. Back to the back side of our sheet, we were looking at these daughter ions, and one of the most common ways that daughter ions form is by alpha cleavage. You guys know alpha. It's the first part of the alphabet. Did you know that? When I started learning Arabic, the first 2 letters in Arabic are alif, ba. And I was like, well, yeah, of course they are. A, B, alpha, beta, alif, ba. They're all just alphabets. Crazy, right? It's crazy that we have a word for the list of letters, alphabet, that is actually just the name of the first 2 letters. It's like when you say, your kid learned their ABCs. That's just the first 3 letters. That's the American or English version of the alphabet, which would be a Greek. Anyways, alpha cleavage, obviously we're talking about first priority, like option number 1, alpha. So what is alpha? Typically, alpha is a carbon of interest. So in a molecule like this, where I have a functional group, my functional group here is the alcohol. This is the alpha carbon. It's the carbon of interest. Carbon of interest or functional group carbon. Because I do hate to say it, but later in OChem 2, we're going to say that alpha carbons are also adjacent to carbonyl carbons, not the carbonyl carbon, but for us, we're going to think of that carbonyl carbon as the alpha carbon. So alpha cleavage is very common. Bonds will break so that the alpha carbon is being cleaved. Daughter ions often form as the result of alpha cleavage. There is a stability that the alpha carbon can give. There's a stability that the that the functional group can give. So if I want to show alpha cleavage, there's two options. One is cleaving the bond on the left, and one is cleaving the bond on the right relative to our alpha position. So let's look through those two options.
So not the OH.
Not cleaving the C to O, but cleaving the carbon of the alcohol. Option 1, let's say that I take the CH3 on the left and I cleave it. No surprise, there are two options for what happens to the fragment when that electron is removed. The CH3 can take the radical, and the alpha carbon can take the positive charge, or the CH3 takes the positive charge, and the alpha carbon takes the radical. All right, I'm going to do some quick math for this structure. 15 for a CH3, 15 for a CH3, 14 for a CH2, 13 for a CH, and 17 for the OH. This isn't hard math, it's just carbon plus 3 hydrogens, 12 plus 3, a methyl group is 15. Carbon plus 2 hydrogens, a CH2 is 14. Carbon plus 1 hydrogen. Again, you are allowed to bring a calculator to the midterm if you want to do this kind of stuff. All right, and then I like to do my math in groupings. So I see 30 and 30 and 14. So that gives me 74 mass per charge. If it's the molecular ion. So actually, I'm sorry, I shouldn't even say that because that doesn't have a charge on it. 74 AMU is the mass of the molecule. Do we see a molecular ion for this structure? Do we see a signal for the molecular ion at 70?
Maybe tiny.
74? I agree. Actually, that looks like it's at 73. And so not really. There's not really a molecular ion for this compound, despite the fact that it has lone pairs.
Are we gonna have to know how to do math like that?
Is that hard math to do?
Well, I don't even know where the numbers are coming from.
Okay. CH3, which is 12 for carbon, plus 3 for hydrogens. 12 plus 3?
So we're just adding the groups?
15, yep. What's 12 plus 2?
15.
12 plus 14. 12 plus 1? 13. 16 plus 1? 17. So that's where those individual parts came from. I'm just looking at each grouping.
So how do we know which numbers to add? Is it like outside in?
Oh, I was just doing my math. 15 and 15 is easy for me to add.
Oh, so it doesn't matter.
17 and 13 is just easy for me to add.
As long as you give the end result.
Yep.
Oh, okay.
But you're allowed to bring a calculator. But I didn't feel like I needed a calculator for this.
And sorry, just like one question. So like with the numbers, it's just going off like atomic mass, correct?
Yes,
Okay, sweet. So we don't have
because we're not weighing this on a scale.
no.
We're using a magnet to bring it to a detector. So we're using the math of the magnetic field strength against mass of the fragment. So it is calculating it in atomic mass units.
So we don't have like a full number set, then you're just like pulling off the periodic table.
We're going to talk about that. Pull them off the periodic table versus pull them out of thin air. I'll answer that in a minute. Okay, so my molecule weighs 74. This possibility of fragmentation on top will give one reading. What mass will it give? What can I call the signal? I can call it the M-15 signal. Why? I cleaved off a CH3, and that radical gets pulled into the waste. And so the signal will show up at what mass per charge? 59? 74 minus 15. 74 is 64. And then 64 becomes 59. So this shows up at 59 mass per charge. Do you see a signal on the spectrum at 59 mass per charge? It's the second tallest. And we can label it as M minus 15.
Why wouldn't the molecular ion appear on this?
What it's saying is that the molecular ion just doesn't form very often, or if it does form, it fragments.
Okay.
And it's just not an abundantly forming fragment.
So it exists, but if it's not, we can always tell by adding the mass of the entire molecule.
You can always predict,
But it might not appear.
but it might not be there. Which is why earlier you guys said, how do you know where the molecular ion is? In theory, it's the highest mass signal, but when you look at this one, do you really see a signal at 74? No, honestly, the biggest one is 73, which means it's the M minus 1 signal that's showing up the most. A hydrogen getting kicked off.
So what's our base peak here is 44?
Yes, I agree.
How do we see that in that?
Where do we find it? Well, let's look at our other one, which is the M minus 59 signal, which would show up at a mass per charge of 15. Do you guys see a mass per charge signal at 15? Tiny. Okay, so out of this option, where I do alpha cleavage on the left, I form the second most abundant fragment, M minus 15. Option number 2, where I cleave the alpha carbon on the right. Believe it or not, there's 2 options. Can you draw the combination of options? Or if you want to, can you draw the 2 possible cations? That's really all you have to show, is because the radicals don't form signals. Can you predict the 2 possible cations that come from this? Yep. Now can you figure out their masses? And do you see those masses on the structure? On the structure? On the spectrum. Good. Oh, found it.
So that means that that's our most abundant dye, because, but then the one we found up there is the second one.
Yeah.
I would say I may be alone in this, but I feel like this is more complicated than IR. I was just thinking that. Am I the only one who thinks that? Yeah? Okay. I think because it's.
Okay, well, how about this? You're never going to need to use the mass spec to determine a structure. I'll give you the structures for mass spec. Yeah, no, that is a good question. Actually, what is mass spec for? If you don't know the identity of your compound, you can put it through mass spec and hopefully find the molecular ion, which means that you'd get the molecular mass of your unknown compound. There is an additional detail here, which is nitrogens. Nitrogens often bond 3 times, which means that they often have just one extra atom added to the system, one extra hydrogen. I don't know if you guys noticed, all of the structures we looked at so far have even molecular masses, 122, 84, 74. The 3 structures we've looked at are all even massed. Most molecular formulas, most molecular structures are even mass molecules. Nitrogen makes them odd mass, so we can learn about nitrogen that way.
I'm so sorry for the bad drawings, but
Great. That's perfect. Yep. 2 CH3s? I don't think it would be 2 CH3s.
Where would the positive would be on the carbon, right? Where would this be on?
Well, you're breaking a carbon-carbon bond.
So it would be on this carbon.
One carbon takes the radical, one carbon. Yep.
Okay.
And then if you are going to show the carbons and like forego bond line structure, then you should show the hydrogens too. So write it as a CH2 plus, or just show it as a stick.
Gotcha. So this would be.
Got it. So it's just a, yeah. You mean-
Yeah, you added
I added it.
and here too.
I did? Oh, yeah, you're right.
What do we think of this big dog?
Yep,
Okay.
that's it. Those are the 2 possibilities. Great work. All right. Option 1, the positive charge is on the alpha carbon. Option 2, the positive charge is adjacent to the alpha carbon. So these would be the 2 cation possibilities. I'm not showing the radicals, but I can if you want me to. On the top, I've got 15 plus 13 plus 17. 17 and 13 is 30. 30 plus, yeah, I agree, it's 45. Didn't you say you got 44 earlier?
No, I said I got 30.
Oh. 45 mass per charge, which is the M minus, well, this guy down here is 14 plus 15. That's 29 mass per charge. So this is the M minus 29, and this is the M minus,
Why is it 45?
I don't know. You tell me.
If the,
Oh, because the base peak is 45, not 44.
it is?
The base peak is at 45. It's dead on the center between 45 and 50. Dead on the center between 40 and 50. Yeah. They're not easy to read, are they? Is there resonance in this molecule, in this fragment, in this cation? Would it be a 2-atom system or a 3-atom system of resonance? A 3-atom system needs a pi bond plus a charge or a lone pair. This doesn't have a pi bond. So it could be a 2-atom system which needs a lone pair and a vacancy to accept a lone pair, and that positive charge on carbon is a vacancy. Here's a resonance form for this structure. There is a resonance form similarly up above a 2-atom system. This is why alpha cleavage is the most common type of daughter ion formation. When the group gets cleaved adjacent to the functional group can often participate in resonance to stabilize the positive charge. So it happens very often that a group adjacent to the functional group is cleaved, and then the functional group resonance stabilizes. Alpha cleavage is very common. Alkyl halides cleave adjacent to the halide. Carbonyls cleave adjacent to the carbonyl, because then that positive charge can be that positive charge can be supported by resonance. All right. The last thing for us to talk about in this realm is isotopic clusters. So at this point, Patrick was asking, I don't need to pull out numbers from thin air. I just look at the periodic table, right? Well, the periodic table does not tell you the mass of an atom. The periodic table tells you the average atomic mass of all atoms. No carbon atom has an atomic mass of 12.01. But that's what you'll see on the periodic table. Carbon, 12.01. Carbon weighs 12.000 98% of the time. And it weighs 13.00 1% of the time, 1.1% of the time, and it weighs 14.00 less than 1% of the time, less than 0.1% of the time. Carbon 12 is the most abundant. Carbon 13 is not very abundant. Carbon 14 hardly exists. 98%, about 1%, and less than 0.1%. So the average atomic mass is 12.01. But 98% of all of the carbons in your structure have carbon 12. What that means is you get a mass spectrum where 98% of the 98% of the carbons forming the molecular ion signal are carbon 12, but 1% are just a little bit heavier. And so we call that an M+1 signal. It's the lightest isotope of carbon mixed in with little bits of heavier isotopes of carbon that show up at a heavier atomic mass, a heavier mass per charge. This is what we call an isotopic cluster. And whether it happens because of the 1% of carbon every now and then popping into your structure, or whether it happens from the 0.1% of H2, just the fact that these heavier isotopes exist means some of your sample is going to weigh a little bit more than the rest. And if you look at the molecular ions we've seen, look at the molecular ion for benzoic acid, 122, and what do you see just to the right? An M+1, a tiny little peak, an isotopic cluster that comes from having these different masses. What do you see at cyclohexane? The molecular ion at 84, and then at 85, an M+1 signal. There is an M-1, and we saw that for the sec-butyl alcohol. Looked like an M-1. That's not as common. That's not an isotopic cluster. That's the loss of an atom. Okay, and sorry, this is under isotopic clusters. Now, you guys, I think, can see that the isotopic clusters that result from carbon and hydrogen isotopes are unreliable at best. It's not like a consistent size at the M+1. It's a bit random. But bromine and chlorine give very consistent isotopic clusters. Bromine exists as bromine 79, 51% of the time, and bromine 81, 49% of the time, which makes us think that bromine has an average atomic mass of 79.90. Bromine never has an atomic mass of 80. Despite the periodic table rounding up to say that bromine on average has a mass of 80. Bromine never has a mass of 80. Bromine half the time has a mass of 79, and half the time has a mass of 81. Which means that when I find a spectrum with bromine, and again, let's just look at a molecular ion, for example. My molecular ion signal has a peak 2 mass units away that is almost exactly the same height, and so we call it the M+2. Half of the molecular ions forming have bromine 79. Half of the molecular ions forming have bromine 81. And those different masses hit the detector at different places, reading as different masses.
Just conceptually, what that's saying is like if we grabbed a handful of bromine and then weighed the average mass of it, it'd be 79.9.
Correct.
Okay.
Correct. If I grabbed a handful of bromine, the average mass would be 79.9. And then if I threw those bromines and let them be pulled by a magnetic field, they would separate by their masses into 2 groups. By atomic mass. Because we're not using a scale to weigh these. We're not getting an average mass. We're getting individual masses. Yeah. This is an isotopic cluster. And for bromine, we say the isotopic cluster is 1 to 1. So look at the mass spectrum for tert-butyl bromide, or you could also call it 2-bromo-2-methyl-propane. Do you see an isotopic cluster for tert-butyl bromide? Label it as M+ and M+2. Are they the base peak for the spectrum? Far from it. What is the base peak? It's 57. Which is actually a structure on your correlation table. By the way, I don't give you that correlation table on the midterm because I just don't find it useful. But on there, 57 could correspond to 2 different things. It could correspond to a tert-butyl carbon cation, or it could correspond to a carbonyl cation. It would make sense for that to be the tert-butyl cation, which has a mass of 57, and could be labeled as M minus what? M minus 79. The loss of bromine shows up at M minus 79 because bromine has a mass of 79.
So how can we use 79 instead of 81? It's because it's...
Right. They just go with the lower mass isotope as being the molecular ion, and then the heavier mass isotope being the isotopic cluster. So here's the ion that formed this. Here's the ion that formed our molecular ion and M+1. I'm sorry, M+2. Notice how I'm just drawing it as one of bromine's lone pairs has been lost. Is that a bromine 79 that lost its lone pair? Yes. Is it a bromine 81 that lost its lone pair? Yes. It's both of them, which weigh different things and hit the detector at different places. Chlorine appears as chlorine 35, 75% of the time, and chlorine 37, 25% of the time, which gives us this false impression that it weighs 35.5 atomic mass units, but it never actually weighs 35.5. The cluster that we get from chlorine is a 3-to-1 isotopic cluster. One of them is present 3 times as often. Tell me.
I was just asking how I made it through Gen Chem without understanding averages of isotopes.
Yeah, you feel like you don't need to understand isotopic averages to get through Gen Chem.
That's true.
Yeah.
But like I didn't realize that it literally will never be 35.5.
Yep. Unless you weigh it on a huge scale.
Yeah, right.
You go into the lab and weigh out a bunch of chlorines, because you're measuring moles worth of them, you're going to get an average, a very nice, repeatable average. But you get down to a tiny number, hundreds of millions, and you separate them, they'll get separated by their masses. A 3-to-1 isotopic cluster. That's what we get. So let's look at this structure for 1,2-dichlorobenzene, or the spectrum for 1,2-dichlorobenzene. The molecular mass for this is 75 plus 70, so 145. Do we see a signal at 145? No, I'm sorry, it's 76 plus 70. So do we see a signal at 146? Yes. What is it? Our base peak. Our base peak shows up at the molecular ion. The problem with this spectrum is that there are 2 chlorines, which changes the probability of what the isotopic cluster looks like. But if we were to form a molecular ion, well, there's a lot of different ways we could do it. It could be one of the chlorines loses a lone pair electron. It could be that one of the pi bonds loses an electron. There's a lot of ways for it to happen, and so it tends to happen a lot, and it becomes our molecular ion. But when this happens, I could have chlorine 35 and chlorine 35 as both of my chlorines. I could have chlorine 35 and chlorine 37, or chlorine 37 and chlorine 35. You see that what I'm doing there is just saying that either one of the chlorines could be the lower or higher mass isotope. And there's the possibility that both of them are chlorine 37. Which of those is the least likely combination? Both being 37, since 37 makes up the least amount. Which of those is the most likely scenario? 35 and 35, just because that is the highest abundance. Despite the fact that one of each happens more often, there's just less of this. So the molecular ion isn't just an M plus 2. It gives us M plus 2, but then this opportunity to get an M plus 4. So you can see that there's this isotopic cluster of 3 peaks in that isotopic cluster. Now, it's likely that one of the chlorines could get cleaved off. And then we form a cation daughter ion where one of the chlorines has been lost. So another major peak comes from the loss of one of the chlorines, which we would label as M minus 35. If our molecular ion, I did all that math and then I lost it. If our molecular ion was 146 minus 35, 111. And do we see a signal at 111? Not just a signal, is it? It's a 3-to-1 isotopic cluster.
You're also saying like M plus 2 minus 35?
Yeah. Well, if you're looking at the M plus minus 35, otherwise you have to do the M plus 2 minus 37. So this is at 111. This still comes from the 75% chance that the chlorine remaining is chlorine 35 and a 25% chance that the chlorine remaining is chlorine 37. We still get an isotopic cluster at 111 because there's still a chlorine present. Liana?
What causes the little lines in between the, like, at 146 or at like 147?
Mostly this. The isotopic clusters that result from carbon and hydrogen.
Okay.
They're going to, every now and then, there are heavier isotopes of carbon and hydrogen, and those just change your mass by 1 unit usually.
So like in between what's being affected by the chlorine is being.
Yeah, and you can notice that there's a ton of little peaks, and we don't look at most of them.
So it's just a coincidence that it's like organized like that.
Yes, coincidental.
M plus 2 on the far right, that's because that's the 37 chlorine, right?
It's one of the possibilities, because this structure was a little bit more complicated than our bromine example because it had 2 chlorines.
Right.
So the M plus 2 comes from one of the possibilities where one of the chlorines is heavier.
And then is M plus 4, they're both 37 because it's 2 plus 2
Yep,
from the base.
exactly. If both of them happen to be heavier.
Then what is M plus?
The molecular ion. And we'll always say the molecular ion comes from the lower mass isotope.
So that's just 35 Cl?
This one here is when both of them are chlorine 35.
Okay. And then the middle is 35, 37, and the right is 37, 37.
Yep.
Then what's the far left?
Here,
This is the common, what is that?
this one,
Yeah.
at 111,
Yeah.
not a molecular ion,
No.
because the molecular ion's at 146.
Okay.
This is the molecule less 35.
Okay.
35 is the mass of what?
The most common.
The most common isotope of chlorine. So if I lose one of my chlorines, I get M minus 35. But because I had 2, Gavin, losing 1 means that I still have 1, means that I still get an isotopic cluster from the 1 remaining.
The lower mass is always the M, even if the higher mass is more prevalent?
Yeah.
Okay.
Yep. And it's not actually very common that the higher mass is more prevalent. You'll notice here the lower mass of bromine is more prevalent, the lower mass of chlorine is more prevalent, the lower mass of carbon is more prevalent, the lower mass of hydrogen is more prevalent. So I actually have never seen an isotopic cluster where the higher mass is more prevalent. And I'll tell you this, a lot of the questions on mass spec come back to isotopic clusters. Can you use the isotopic cluster to identify that bromine is present or that chlorine is present? That's one thing that I look at the most with mass spec. Or can you predict a molecular ion structure? Can you tell the difference between what will register as a molecular ion and what will not register as a molecular ion? So isotopic clustering, you're just going to see it with bromine and chlorine. That's the only time we're talking about isotopic clustering. More questions? Sorry? I don't know that it's common for the rest of the halogens. And we know that it's not necessarily the most common thing for all of the elements. So yeah, I think coincidental that it's two major isotopes that are different by 2 mass units. Do you still feel like this is harder than NMR and IR? Interesting. Okay, we're very split on this.
Are you gonna give us the
On the spectra, I will give some of these numbers. And I didn't do that on this worksheet, except for on the very first one. If you look at the front page, you can see that I've done M plus, M minus 15, M minus 29, M minus 43, M minus 57. So I went through and I showed all the different ways that 2-butanone can form a molecular ion. I showed what the radical cation looks like, except I didn't draw the resonance. I showed what another alpha cleavage looks like. If I don't give M minus over the relevant peaks, then I will typically write the signal over the peaks. Now I know that we're running out of time, so I don't think you guys will be able to do this in class. I'll post an answer key with this. But I thought I'd give you guys practice problems determining structure from spectra. Sorry. And I've demonstrated what it looks like to take a mass spec and draw the to write the masses over the signals so that you guys don't have to try and guess at that. So this should be good practice for you. You're welcome. In preparing for the unit test this weekend. I had hoped that if we had more time, I could actually have each of you work in pairs to pick a structure, to pick a set of spectra and derive the structure. In 5 minutes, I don't know that you will really be able to get to the structure. If you can do it in 5 minutes, I need to change the unit test. So the rest of the time is yours. If you want to get a head start on this, my advice would be start with degrees of unsaturation so that you know whether you need to look for pi bonds or rings. Then analyze the IR. Find the bonds that are predicted by the IR. Then go through the NMR and cover it. The mass spectra might not do anything for you. So what you could do is just practice, once you've determined the structure, draw a molecular ion.
Can you say again what you were recommending steps were?
I'll write it down. First, degrees of unsaturation. That's the 2 chicken rule. To look for whether you need pi bonds or rings. Then I would say analyze the IR, figure out what bond types are present. Then combine with the NMR to figure out the structure. Then what? Oh, predict a molecular ion. Good luck on your unit test this weekend. And I'll be around for the next 5 minutes if you want to start on one of them and ask questions. I did that in my lecture in the spring once. I was like, well, I'm done early, so the rest of the time is yours. Oh, and you have a minute and a half.
Not that early. Did you guys, Quinn,
Will the equation for degrees of unsaturation?
Yes. Our lab
Given that on our
yesterday
note, on our card?
Yeah, the equation would be a good thing to have on your cheat sheet, unless you can remember the 2 chicken rule, which is multiply by 2, add by 2, divide by 2, subtract 2 times, add 2 times.
oh yeah.
So there's a lot of,
Stop working for
I don't think it's too hard to memorize, but it doesn't take up a lot of space either.
And then he broke it.
Yeah.
So,
Who is that guy?
we did the lab, but the lab did us, really.
The lab did you. He is our instrumentation coordinator.
Oh, very nice.
His job, well, when he first started here, his job was just to manage all of our equipment
Yeah.
and our instruments. Then the lab coordinator retired, and they didn't replace the lab coordinator, and they just split the responsibilities between two people. One of them fell on him. So he's now the instrument and lab coordinator. What he really does the most is like ordering the chemicals and consumables that we need in the lab and maintaining our equipment. He subs a lot too. He'll fill in for instructors.
He subbed for Chris yesterday.
That's right.
And it was,
And I had him come in on Tuesday for my lab because the NMR wasn't working. I had him come in to try and fix it. So he knew that it wasn't working.
he knew that it wasn't working, but then he got it to work again.
Yeah.
And then when we were in lab yesterday, it stopped working again. And so he just printed out like a practice NMR sheet for us to all work on. But
Good.
it was, I mean, the lecture part, it was kind of incomprehensible, which I hate.
How much did he lecture?
45 minutes, maybe an hour. It was a long time.
On each of them?
On what IR is, what NMR is, and then about the machines. kind of.
Sure. Instruments.
But I can't, yeah, sorry, the instruments, but I can't really say I fully understood what was happening.
Yeah, that's how it goes.
Yeah.
That is, I mean, that's instrumentation in a nutshell.
Yeah.
One of his PhDs is in spectroscopy.
One.
Yeah, very smart guy.
How many does he have? 3?
2.
So many PhDs.
Organic chemistry. So he got his PhD, I think, in Moscow in organic chemistry. Born and raised in India, got his bachelor's in India. Moscow gave him his PhD in organic chemistry, and then he did a stint in Belgium, and was working on NMRs. Yeah, he does. He learned both of those languages.
Which languages? Russian and
Yep.
English?
English, Russian.
German and French doesn't.
Yeah.
It's Dutch and French.
What's Flemish?
Flemish is like Belgium's like original language because like there's like they're divided between the French speaking and the Flemish speaking. The Flemish is like we're the original Belgians.
Who speaks?
Flemish.
It's Dutch. It's very similar.
I don't know that he learned those. Do you know that he learned those? I think he learned French and German, but I don't think he speaks those as well as he speaks Russian.
A lot of German speakers in Belgium as well.
Sure. And just chemistry in general was really developed by the Germans, sometimes unethically. There were Nazis that did a lot for chemistry.
Yeah. I mean that's like how we got like a lot of like medicine.
Yes, the Nazis at no moral dilemma paved a huge path into science.
And Japanese.
Did I say that right? At no moral dilemma to themselves. Yeah, with a huge moral cause, but with no moral perception, paved a huge path into science. Asperger's was named after a Nazi. It's not called Asperger's anymore. I believe that's predominantly why it's not called it. I don't know what it's called now.
They made it more of a spectrum instead of just.
Oh, it got incorporated into ASD. Because it belongs there, and because it has no place being named after a Nazi.
And also they're trying to get away from like biomedical terms being named after men because they've always been named after men.
Thank God.
Like tons of female anatomies named after men.
Mm-hmm.
So
Yeah, the something in your ear was named after a guy. No, the tube, eustachian tube, which honestly sounds like it could just be biology.
Sounds like German.
I want to say something in the reproductive system, the female reproductive system, is also named after a guy. Fallopian is named after a guy.
Mr. Fallopian.
Have a good weekend, Andrew.
Fallopian? I think that's kind of a sick name. My last name is Fallopian.
Yeah, it is.
I mean there's like a doctor.
Gabriel Fallopio.
Sure, Fallopio, and so his tube is fallopian. The Floodian.
Fallopian.
There's a doctor who does like vasectomies who seems like patriarch Dr. Dick Chong.
No.